Okay, let's try to look at a design where we would maybe put some fabric peripherals in, like a UART. And we can choose our language. The language can either be Verilog or VHDL, doesn't matter. What matters is when you use any of the configurators or after we synthesize, then we'll take the EDIF netlist out of synthesis and we'll create a structural netlist that matches the language you choose here. I'll say next, and I'm going to choose a device, and let's choose a device that's on the AVNet board. So that's the M2S01010S in the 144TQ package, and that happens to be a commercial device and the standard speed grade. And I'll say next. And default I/O technology, you can leave this if you want to. The I/Os are organized in banks. They support different I/O standards. When we synthesize, we put in generic I/O buffers, and you can change them later. But if you were using an I/O standard, maybe LVCMOS 1.8 or something, and all of the I/Os were the same, you could just change it here if you wanted to. PLL supply voltage can be one of two values, 2.5 or 3.3. You have to make sure the software matches what's on the board. The power on reset delay, there's a power on reset circuit in the device that keeps the device reset while everything is coming up, like your power supply. So what you're specifying here is what the ramp time is for the power supply, so we hold the device reset long enough. And then we have something called system controller suspend mode. There's a block called the system controller. That reset controller I mentioned is part of the system controller. The system controller includes a JTAG interface. We use that for programming when we use the Flash Pro. And there's a lot of other services like the flash freeze mode you can use. In some applications, people don't want to use the system controller when the device is operational. So if you check that, it just disables the system controller. And the only way to use it again is to either power cycle the board or reset the board. And then when I come in here, I'll see design templates. And if you're doing a fabric only design where you don't use the Cortex or any peripherals, you can say none. If you're using the Cortex, then we have really two different tools you can use. We have a wizard tool that I'm going to show you called System Builder. It's our newer tool, kind of the direction we're moving in. We have an older tool that only configures the microcontroller subsystem called the MSS configurator. But if you use System Builder will put everything in for you that you need. So we'll just choose System Builder here. And then we have a use standalone initialization for MDDR, FDDR, and SerDes. So MDDR is the MSS DDR controller. It's a controller for external DDR memories. FDDR is a fabric DDR controller. It only exists in two parts, the 050 and the 150. And then the SerDes are the high-speed serial interface units that are on the 10, 25, 50, 60, 90, and 150 devices. So by default, we use the Cortex when it boots to initialize the registers in those blocks if they're in the design. If you want to, you can use what's called standalone initialization, and we'll create initialization logic in the fabric so that you could have separate initialization blocks for each of those. It uses some more fabric resources, but if you want to separate different blocks of the design, you can do that. Most people just leave that unchecked. So I'll say next, and here I could import source files if I had any, but I don't. If I say next, I could import constraint files if I had any, but I don't have any of those either. So I'm just going to say finish. And this is something new in 11.7. We've modified the way you enter constraints, timing constraints that can be used for synthesis and for layout, even physical constraints. There's a new constraint manager. You see a picture of it here. So you can use the classic flow. That's the same as what we had in 11.5 and 11.6, or you can use the new constraint flow. I'm just going to use the classic flow now because this design really isn't going to have much in the way of constraints anyway. So let's see. We'll just call this My System, I guess. You can name your system anything you want, but it has to be a legal VHDL or Verilog name. Hence, if I try to leave an underscore at the beginning, for example, it should give me an error. She didn't like that kind of stuff. Probably would have caught it later. So when I click OK, the System Builder tool is going to open. This is a wizard tool that lets me go in and specify various different blocks I want to use in the design. So here I could enable the external memory controller. That's the DDR controller I mentioned. And you can have either a soft memory controller, so you have a memory controller in the fabric that connects to SDR memory. This particular package doesn't have the DDR controller enabled, so you see it's shadowed out. We can use the on-chip flash memory if we want to, the embedded flash memory, and we have some other options for the microcontroller, the watchdog timer, the peripheral DMA, and the real-time counter. So if you want to use those peripherals, you would check those. I'm just going to disable the memory and not use it. I'll say next. Here is where I could create a partition for the flash memory. So let's call this program store. And you can import the configuration from a file, but if you don't have it, if this is where you're going to have your code and you haven't developed the code yet, you could just say that it's a placeholder. And you can pick out a starting address and a size and number of words. I'll just put in 8192 just for have something in there. You'll see I can also say use as ROM. If you wanted to, you could have a partition that contains data that you don't want to have the Cortex be able to change. You can only change it when you program. So we could create a ROM if we want to. So there's my partition. I could come back later on after I've developed code and I could put the code in there. I'll say next. Now when I get to this page, the peripherals page, I'm going to see MSS peripherals. These are hard peripherals that are in the microcontroller subsystem. And when I say hard, I mean they're implemented as standard cell as opposed to using the FPGA. Then I also have some soft peripherals over here that could be put in the fabric to enhance what's used with the MSS peripherals. And you see I have something called the FIC, the Fabric Interface Controller. That's an interface between the microcontroller subsystem and the fabric. And I could put peripherals over here. So I have MSS, FIC, MSS master subsystems. That means the Cortex M3 is the master. And I could bring in peripherals. I have SRAM, Core I2C, Core SPI, Core GPIO, Core Timer, Core UART APB. So if I wanted more timers, more GPIOs, more I2Cs, I could just drag those in, drop them under the interface here where the MSS is the master. And I could even change the quantity if I want to. Let's say we wanted to put 3 UARTs out here. So I've got MMUART 0, MMUART 1. I have 2 UARTs in the MSS, and I got 3 more UARTs that are going to be in the fabric. And I can configure this. I'm going to check and see what the configuration is here. So right now it's set up where the configuration is programmable, and there is a TX and RX FIFO, but it's disabled, so we can enable that. That may have been an issue that you ran into. I could go through here and I could configure some of these peripherals if I wanted to, and I can disable some too if I didn't want to use all of them. The other thing I could do is I could put a master interface over here, and I could have a master in the fabric, and my fabric master would let me access these peripherals so that I could be connecting to the peripherals in the microcontroller subsystem or the external memory. And you could actually have a master in the fabric that ran simultaneously to the Cortex running. Got an error message. That was indicating an error. The reason for the error is there's some specific, some things that are specific to the particular package that we're using, where some of the connections that have dedicated IOs aren't available, and I have to connect it to the fabric instead. This is one of the smaller packages, the 144 package. And by going to that small package, they've disabled some of the IO paths. So we'll connect these into the fabric instead. Now the problem's gone. Here I'm specifying my clock rates that I'm going to use in the design. And we have some internal oscillators that we could use along with PLLs to generate frequencies, or we could bring a clock signal in from an external pin. Not all of the boards that we sell have external oscillators, or maybe they only have one, just to keep the cost down. So you've got some choices where you could bring it in from some input pads, or you have some various different oscillators, and I'm going to use this 2550 megahertz RC oscillator, which is an RC oscillator that runs at 50 megahertz internally. And I can use that as the reference clock to the PLL, and then I can generate different frequencies. So I could specify the Cortex M3 clock. Right now we're saying 100 megahertz, and I could take that higher if I wanted. One thing you notice, if you click on the name of the clock, it highlights so you can tell which clocks you're looking at. We have some clocks here for peripherals, and these right now are just all defaulting to 100, but I could change them. I could make it 50 or 25 or 12 and a half if I wanted to. Normally, because these are all done in standard cell, you just leave them the same speed as the Cortex. And then here is my FIC clock. This is that fabric interface controller I mentioned that allows the interface between the microcontroller subsystem and the standard cell portion with the FPGA fabric. And this is where our UARTs are going to be placed out here, and we're going to access them through the FIC. So I can specify the clock rate here, and I could divide it down. I can divide by as much as by 32 if I want to. And depending on the peripherals you put out there, you may need to divide those down. I'm going to say next. Then I have a number of options here that have to do with the microcontroller subsystem. The behavior of the watchdog timer. You can even expose it to the fabric if you wanted to. If we used the block called the real-time counter, it's a block that does calendar functions, so you can do time and capture time and put timestamps on things. You would specify the clock source there. I'm just going to choose the 1 megahertz oscillator because we have a sample project that uses that as the source. You can bring in what we call wake-up interrupts, and you can take one to the fabric and you can use one from the Cortex. So you could put the device in a low-power sleep mode, but set the RTC before you do, and then have it wake up after a certain amount of time. And then you can also use it just as a match if you want to. It's really just a counter with a match register. Another way of using it, if you don't want to use it as a calendar, is to just use it as the counter with the match, and you can expose the match signal to the fabric if you want to. So what you could do with that is you could just like use it for some kind of a waveform or something that you might want to take into the fabric. Peripheral DMA. We have a DMA controller that will move data between peripherals and memory locations. We call it the peripheral DMA, and you can expose the DMA ready signals through the FIC if you want to. That would allow logic in the fabric to access the DMA ready. Maybe if you had a master in the fabric, it might be using the DMA controller. It can set it up and use it. There's some options for the Cortex M3. We have a memory protection unit. We can block off certain memory areas for security. There's a built-in timer called the SysTick timer, and there's some settings to use the SysTick timer as far as the calibration register and what the clock rate is relative to the Cortex. There's various other sleep events and things that you can expose. We have a cache. We have a data cache. I'm sorry, we have an instruction cache, not a data cache. And by default it's disabled, but you can enable it, and then you can specify the cacheable region size. And we can cache from the flash memory or the ESRAM or even external memory. And then we have something called the AHB bus matrix, and we have some different parameters here. For starters, we can remap memory, either ENVM, ESRAM, or the external DDR memory to address 0, so the Cortex can execute from there. By default, we map the flash memory there. We can also do this by writing registers, and that's how the Cortex, or how the SoftConsole debugger does it. You have remap region sizes and base addresses that you can set. And then we also have something called the AHB bus matrix, which is a subset of a cross-point switch that allows different masters to be executing simultaneously, and they can access different slaves. SmartFusion2 can have up to 10 masters and up to 7 slaves, and all the masters could be working simultaneously. And we have some parameters that you can set that have to do with the arbitration and how long masters can access a peripheral before they have to give it up. We have the ability to enable error detection that we call SECDED, single error correct, double error detect, for various different memory blocks. This is a reliability thing. Should a particle strike change the data, we can detect 2-bit errors and we can correct single-bit errors. So we can go through and we can enable the EDAC on different memory blocks. There's 2 ESRAM blocks, and we have the CAN controllers and the DDR and the flash memory and so on. And then if you do enable the EDAC, then you can generate interrupts if you want for 1-bit errors, 2-bit errors, or both. So depending on the application, some people may enable the EDAC. Then we have a bunch of security options that are available in some devices. I mentioned that AHB bus matrix. So here are some masters and here are some slaves, and you can prevent groups of masters from accessing certain slaves. We have 3 groups of masters, and I could prevent a group of masters from accessing certain slaves if I wanted to. So if I had some data in the flash memory that I didn't want, maybe a fabric master through the FIC to be able to access, I could block it off. I could prevent that. This is only in the devices that have this S suffix over here. So in some devices, if they don't have the S suffix, you'll see this is shadowed out. It's one of what we call the data security features. Then when we say interrupts, the tool is going to look at what we wanted to put in the fabric, and it's going to show me interrupts that are going to be generated. I put in 3 UARTs, and I have these signals: TX ready, RX ready, parity error, overflow, and framing error, and they all are going to be ORed together to generate interrupts. We can take 16 interrupts back to the cortex from the fabric. Through the interrupt controller, 16 of those interrupts come in from the fabric. So we OR these together, and if we got an interrupt from UART 0_0, then we could read the control registers and figure out what the interrupt source was. So this will tell you which interrupts are being generated. And then finally, I have my memory map here for my peripherals. So this shows me where the peripherals are located. And there's actually an aliasing scheme, so I can address UART 0, for example, at either 5000 0000 or 3000 0000. And you can change this around if you don't like it. You could just use the pull-down menus, and you could reorder them if you wanted to. I could put 2 at the top and put 1 in the middle and put 0 at the bottom. So you can kind of, you have some limits, but you can modify the memory map a little bit. Then when I say finish, it will take a few minutes, but it will generate my entire design. So it's going to have the configuration for the microcontroller subsystem, but it's also going to have all of the peripherals in the fabric, those 3 UARTs, plus some interface logic that's required to go through the FIC and access those UARTs. And it's also going to put in my RC oscillator and a PLL to generate the clocks that I specified. So this will take a minute. When we're finished, we'll see a symbol in the Smart Design canvas, and then the next step would be to connect those pins to ports, or maybe bring other logic in and connect to that logic. And then once I've done that, I would go through and I could simulate the design if I wanted to. Then I could synthesize it, and I could go through the layout step and ultimately program the design. So here's my symbol, and I have groups here for the UARTs, and if I wanted to connect those to pins, for example, I could just hold down the control key and select all those pins, and then right click and say promote to top level. So that creates a symbol here. When it's at the top level, it means it's going to be a port on this component, and if that port happens to be the very top level, then when you synthesize, I/O pads will be put in. Fab reset in. I could have a reset from the fabric that resets the microcontroller subsystem. I can't leave that float. So if I don't want to use it, I could just right click and I could say tie high. If I say tie low, it's going to always be reset, so I don't want to do that. I could also promote it to the top level if I wanted to. Maybe I want to put it connected to a switch or something like that, but I'm just going to tie it high. We have a number of other signals here. Because I had all of my MSS peripherals, I didn't disable any of them. So you see I have my I2Cs and my UARTs and everything, and what I need to do is I need to connect those to pins if I wanted to connect them to pins on the board. And I can just drag and select a bunch of pins at one time, and then right click, and I lost them. Right click and say promote to top level. Then I have some other things. There's a power on reset, there's an MSS ready. These are signals that come out of the reset controller. The idea here is that when you first boot up the SmartFusion2 device, the Cortex runs some boot code. It writes registers for things like the DDR controllers if you're using it, or the SerDes blocks. So it's not instant on like the Fabric is, because the Fabric has a flash interconnect and it's non-volatile. And when you turn on the power, the Fabric's ready to go. The Cortex takes a little bit of time. So we have some reset signals, and you could hold off logic in the Fabric if you needed to, so it didn't maybe try to access the MSS when it wasn't ready. If you're not using those, you could just mark them unused. And I'm not using them here, so I'll just say mark unused, and it'll put a little X symbol there. Here's another this and it done. This is another one that I really wasn't using. I'm just going to delete this top level pin. Now just mark it unused. Now for outputs like this, if I didn't mark those unused, I won't get an error, I'll just get a warning. But you should always look at warnings. Inputs that are floating will give me an error. So now when I'm finished, I could just click and it will generate my design. The other thing that I could do is, just so you can see what System Builder did, is I'm going to close this, and I'm going to go over here to my system_SB. This is what System Builder created. And I'm going to right click, I'm going to say convert to Smart Design. And when I convert it to Smart Design, it's going to open it, and you'll see all the components that were put in. Okay, there it is. Now it's a little hard to see. It kind of helps. You can expand all the windows here. Or if you click right there, you can just detach that window entirely. Kind of nice if you have two monitors. So we can make this a little bit bigger. And what we have is, let me zoom in a little. This is the microcontroller subsystem. If I double click on that, it will open that MSS configurator I mentioned when we saw the wizard to create the project. And when the MSS configurator opens, that's right, it's open back here, you'll see a box for every single peripheral, and this was originally how we used to do it. You had to configure every single thing individually. We made it a little easier by using System Builder. I put in a reset block. This is the oscillator and the PLL that generated my clocks going in. Here are my Fabric UARTs. So Fabric UARTs. These are in the FPGA Fabric. They connect through this Core APB3 interface that connects through the Fabric interface controller. So these are all mapped into the memory space for the Cortex M3. And then we have a bunch of OR gates. This is where we had the signals that came out that we ORed together to generate an interrupt. And if you could look back up here, these are all the 16 interrupts that I mentioned, and some of them get brought back from those OR gates. You can see one here. There's the output. So we OR a bunch of those signals together. So if any of those signals are driven, the Cortex will get interrupted, and then it would go out, and the interrupt service routine would read the control register for the particular UART, and then it would figure out what the source of the interrupt was. So you can see that when you use System Builder, not only does it configure the microcontroller subsystem, but it puts all this other logic in for you. So you don't really have to think, oh, well, I want some UARTs, so how do I put them in, and do I need this block or that block? You just stay in the wizard, You say what you want into Fabric, and it will put in all the logic that's needed. You don't really have to open this view. I just did it to show you that view. Now, once we've gotten to this point, then we would go to the design flow, and we could synthesize it. You can even simulate it. We have a bus functional model for the Cortex, so we have some scripts, and you could actually simulate writing to these UARTs and make sure they work. Make sure the connections are all correct. You could even, because we have an RTL model for the UART, you can see in simulation, you actually see the data coming out. You could connect the transmit and receives together on different UARTs if you wanted, and see if I wrote something to this UART, do I receive it on that UART, and so on. You can do all that stuff in the script. It's kind of useful if you have external components, and I think particularly you could create your own logic to put in here and connect through the FIC, and then I think the BFM simulation is really useful. And then you would go through and you would synthesize. That'll give you a net list that you can run through layout, and then you would go through the place and route step, which will ultimately give you a design that's been placed, and then we can generate our bit stream and we can program the device. So let's see, if we look at this guy now, this guy should have the configuration set up for the buffers. I think maybe in your case, yeah, see, maybe it was disabled. By default, the FIFO is disabled. Okay, so now that we have our project here, assuming we've gone through all the other steps to synthesize and run layout and that sort of thing, ultimately you're going to want to develop a firmware project. And in 11.7, what you're going to do is you come down here and you say export firmware. And you see you also have a configure firmware course. So if we open this, we right click and say open interactively. It'll ask me if I want to save that because I didn't save it. And this is where I would see a bunch of drivers. I don't see any drivers in here. They're all shadowed out. So let's just download them quickly. I'm going to see drivers in here for the peripherals that I have in my system. And I'm also going to see the SimSys and everything. So what I can do is I could create a sample project from here. And I could use that sample project in SoftConsole. I also have to export the configuration drivers, and that has to do with things like our clocking that we set, because the sample projects, they just use kind of some generic settings, some default settings that are the same for every sample project. You have to make sure that the sample project is in sync with your SmartFusion design. So let's say I wanted to create a sample project to use one of those UARTs. I could right click on this and I could say generate sample project, and you see we have Cortex M1 and Cortex M3, and we have SoftConsole 4.0. I'll just choose hold transmit, okay? This will create a folder called SoftConsole under our project here, and it's going to create a little sample project, or it's going to create a little project that has a SimSys, it has drivers, it has the HAL. In the SimSys, it's going to have those linker scripts. It has a little main.c. It has a platform.h, but I'll show you a gotcha about that.
Okay.
Okay. Well, hang on a second. Now, the other thing I have to do is I have to export the actual driver config. So that project we just created, you can see it over here. Sometimes you have to say refresh design hierarchy. So now I have the SoftConsole folder, and you see this is my project, but you see there's some files here under drivers config. These are the configuration files, but these are just kind of generic. So what I have to do is I have to go down here under export firmware, and I say export firmware, and you can create a sample project, but this is sample projects don't exist for SoftConsole 4.0, so I don't want to do that. What I want to do is just export the hardware configuration files, and I'll say OK, and it will create these under my project, and it will create them in a folder called firmware. So you see now I have a drivers config here, and my sample project has a drivers config, and what I have to do is I have to open this project in SoftConsole. I'll show you how to do that in a minute, and then I have to import these files here. The other thing, you notice that I have a platform.h that just opened up, and it shows me the address of all of my Fabric UARTs and things. It has the address of everything, but all you really care about is the Fabric peripherals. Now I have a platform.h right here, except if we look at these, I'll show you a trick I learned too. This is kind of nice. I can right-click and I can say make a new group like vertical or horizontal. So I can look at the memory map over here, and I can look at my platform.h, and you see that the base address isn't necessarily the same. Core UART APB0. I guess it did call it. I guess it did pick the right one in this case. No, it's 5,000, 5,000. So I'd have to modify this, and I can modify this right here, looking at the memory map. Okay. Well, we do that 5,000, 5,000, 2,000, right? So the platform.h that gets created is kind of a generic platform.h as well. Okay, but we've corrected that, and I can even move that to the previous group and go back, and I can see my design flow. Now let's go over to SoftConsole. We had it open earlier. We're going to close this project. We're going to create a new workspace. So I'll say other, and I'll try to go out and find my project that I had here. UART. We'll go down here to SoftConsole. And I'll say OK. And disappear for a minute. Come back. Now SoftConsole's open. I pointed that workspace, but I have to import the project. The file menu, I say import, expand general, and say existing projects. Then I'll say next. I have to navigate right out to where my workspace is again. Fortunately, it's kind of selected. So there's the project right there. And if I had generated more than one project, I would see them listed here. Then I can say finish. So now, here's my sample project. Should have the platform.h that we just edited. So that's good. But remember, we still have to update the driver's config right here. Because among other things, if you looked at the system clocks, they probably don't match what we did in the design. In fact, you see these different clock rates here? We had 100 megahertz for everything. And if I'm using the UART, that's going to mess everything up if I have the wrong clock rate. Right, so I have to import those. So I'm going to select the file, the project name, and I can right-click. I can say import again. And this time I'm going to say file system. I'm going to navigate back to my Libero project again. This time if I just choose Fabric UART, I'll see Fabric UART there, and then could have done firmware. We made it easier. But I could choose drivers config, bring it into my project. As I finish, oh shoot, got it in the wrong place. Let me try it again. I didn't go down far enough when I did it, so I'm going to say import file system. Here to computer, C, Microsemi, Fabric source files training, Fabric UART. I want to go down one more. I want to get onto firmware here. So I'm going to choose drivers config. I'm going to say make sure it goes into project again. Say finish. Here he's asking me if I want to overwrite them, so I'll say yes to all. So now you see those clock rates are the rates that we had when we configured everything in the microcontroller subsystem. Actually, it's in System Builder that we did that. So these drivers config files in a sample project are just generic files. So you have to overwrite those. And the platform.h is kind of generic too. But you can, when you generate the sample project, you can see that, and then you can look at the memory map in Libero and you can modify it. So that's what we did. So we had the right addresses. And now we have a main.c. So this just writes out little messages to the UART. But you know, now I can be exercising that UART that's in the fabric.
I see. Would you say then, since you can export a SmartConsole 4 template project, exporting one of these example projects for any of the additional hardware you put in, you can just use that as your template project?
You can do that. You could use that, and you could come out here and you could modify this main.c if you wanted to. The only thing that you might have to pay attention to is I only have the driver for core UART APB. So if I wanted to use the SPI or something like that, there's other drivers I would have to configure and bring in because.
Can you export them at all from Libero anymore? Or?
Yeah, you can. You still can right now. You can go out to my design firmware. If I open this up, I can still create the cores today. You would just select the core, and if you say you can generate it, and you need to do a sample project, or you can just generate. If you just say run, it will generate all the firmware cores for you.
In just a folder called.
So let's see if I just say run here. Because they did take that on 11.7, so all I can do is do the sample project here. What I need to do if I want to generate the drivers, if I wanted more drivers to put in here for other peripherals, is I would have to use the firmware catalog. You can launch the firmware catalog from the start menu, and it'll be under. There should be one for 11.7. 11.7's on here. I'll just show you for 11.6 or 11.5. It's the same thing. You would go to the firmware catalog, and this will open, and you'll see
all the drivers.
I'll just say no. So the firmware catalog is going to show you drivers for fabric peripherals. Those will be things like the say core. You scroll down further, we have things for SmartFusion, our third generation flash families, and then SmartFusion2. So you can generate a driver here. You can just right click and say generate. Now one thing you can do that sort of helps if you're going to do this, if you look in the help under the firmware catalog, it tells you how you can generate a launch configuration in your IDE and how you can run it from SoftConsole. So you can go to SoftConsole and you can say run configurations, and you can create a new run configuration that would launch the firmware catalog right from SoftConsole.
Awesome.
The thing that's nice about that, if you run the firmware catalog from SoftConsole, when the firmware catalog generated these drivers you need, it would put them right where you need them.
Okay.
It would put them right in your project.
I see. And those drivers, the only thing to bring them up to functional, make them functional, is just update the memory map, and that's it. The memory locations for.
Yeah. All you need to do is, there's function calls to them. So, give me an example. UART init, UART send. If you want to know where those are, if you just highlight something and then right click and say search text and say workspace, it'll show you there's a little search result, and it'll show you. That's how you can find where these are. So you see something in a main.c, you're not sure where is that exactly, what's the driver. If you see the driver, there's comments, there's more information, and then there's even a user guide for the driver, so you can get even more information than that. So when you look at a sample project and you look at the main.c, if you just use the search function like on UART init or something, then you can understand where that is. And here's some things that are in the HAL and things, but initially you may not know where that is. So you can just do the search, and it'll help you find out where those are, and then you can learn more about them. You get an example of how you use the drivers and so on.
Okay. Is a correct workaround, say you don't want to export all the drivers manually, could you just export the firmware to a 3.4 project, then copy and paste the drivers?
Yeah, you could do that. If you wanted to do that, you could create, go back to export firmware, and we could say export firmware, and we could say create a project for 3.4. Let's just do that. SoftConsole, do I want to overwrite the existing directories? Not really. But let me do it somewhere else. Oh, I'll just call it. try to put it in a different folder. That way, because I have the project open in SoftConsole. What this is going to do is this is going to create an entire project, but it's for SoftConsole 3.4, and SoftConsole 3.4 and SoftConsole 4 projects are not compatible. But what you suggested would work. It will create all these drivers, and then you could just bring those drivers in. The drivers are toolchain independent.
Okay.
So you could still do that. So you see what you would get in that case. I did this right. So there's my SE34, and we made a different type of project here too. We made a project and then a reference project here, but there's all your drivers right there. You can just bring all those in. So that's another way you could do it.
Okay.
You just have to make sure you don't try to open this project in SoftConsole 4.0 because it won't work. But the drivers would be okay. You could just bring all those in. Perfect. So that's another way you could do it.